Good day, everybody. So let's take a look at certain topics of the day that are relevant to introductory organic chemistry. And we are going to get right into the middle of that. And the goal for today will be to combine review things with many different layers of knowledge from the past that we have developed so far. So, and then what we're gonna focus on today is just a few topics, honestly, but they will be quite broad and rife with details. So we're gonna take a look at, first of all, let's start with the Zaitsev's rule, because it's kind of like a singular topic, I would say. And this rule is going to be our item number one. It's kind of important because this can pertain to a lot of substrates or reactants in organic chemistry. But again, this rule is kind of like limited to a specific reaction, right? So specifically, we are looking at the application of Zaitsev's rule to the dehydration of alcohols, right? So what we're gonna do with is just actually kind of like become a little bit more advanced in this case, and we'll apply some thinking processes as well. So like once we make decisions guided by this rule. So let's start with number one, right? So number one will be looking like that. So you have some sort of alcohol, which is gonna be like this one. Let's say we have the OH. It happens to be, as of now, a secondary alcohol, right? And let's imagine that you have the structure like that. So I'm going to add a little bit more features here. So actually, let me just like move things a little bit around. So we're going to have the alcohol like this. Let's see. So that's going to be OH here, then the hydrogen there. So that's something that I'm drawing to show you, to get you thinking about how things will be going. And then let's imagine that we are going to have phenyl rings, right? So because this is something that is quite popular in organic chemistry, as well as medicinal applications as well, right? So I'm saying that because in medicine, you have medicines, right? And their molecular structure of medicines can feature aromatic rings. So that's why we need to be concerned with them. All right, so now let's take a look how dehydration takes place in these circumstances. So when we look at dehydration, we need to keep some things in mind, which will guide us from the reactant to the final product, right? So like in the course of dehydration, we are going to remove water from alcohol, right? So how is it going to be done? So this is going to be done in the following fashion. You are going to remove HOH, right? Or H2O, in other words, by removing OH from one carbon and removing H from the adjacent carbon, right? So it's not like any like random carbon that potentially can have an H, right? So we have a requirement that they need to be adjacent, and those two carbons, from which altogether OH and H will be removed and dehydration will happen this way. So that's one option. So then if you look at this carbon with OH, right? So we found one, at least adjacent carbon to this carbon, right? And then we can mark them maybe like carbon 1 and 2, right? So they're adjacent. So one of them will lose OH because it has OH in the first place. The other one will lose H because it has H at the first place. So now, if we look at other carbons, so we can find out that there is carbon number 3. Let's number it number 3 randomly, which is adjacent to carbon number 1, right? One bond away, adjacent. So if you assess carbon number 3, however, you will see that it has 1, 2, 3, 4 bonds to like other carbons in this case. And consequently, we will deduce that there is no more hydrogens attached to this carbon number 3, right? Because it has maxed out its valences. So you cannot put like a hydrogen here. Consequently, you cannot remove the hydrogen here because there is simply no hydrogen on carbon number 3. So you have really only one option to perform the dehydration, so by removing OH from carbon 1 and removing H from carbon 2. So let's see what happens next, right? So you are going to apply your conditions, right? The reaction goes in H2SO4 as the additive or the catalyst. So it happens to be at like carrying, it happens to be going under relative high temperature of 180 degrees Celsius. And now we are going to show our products, right? So first of all, so you know, in general, that you're going to make an alkene out of the alcohol upon the dehydration of the said alcohol. So we're going to redraw some things, and some things will be new, right? So let's be careful with the carbons. So this carbon loses OH, so this carbon loses H. So, and then other parts will kind of like stay the same, right? So this is what we have. So now, if you look at this carbon originally number 1, it used to have hydrogen, right? So we have like one bond, the second, third, and then consequently we will deduce that there's going to be a hydrogen attached to carbon number 1, because the carbon number 1 has to have like 4 bonds total. So next, let's take a look at carbon number 2. It has 1, 2 bonds, which are clearly visible, right? So, but we also know that the carbon has to have 4 valences available to it. So consequently, what we can deduce from here is that the stuff that's not shown is 2 more single bond, 2 hydrogens, right? So that's things which are implied, right? Looking by the position of the carbon. So 2 bonds are clearly visible. So if there is a double bond, it will be clearly shown, but it's not, right? Consequently, we can imply, it can only be implied that there are 2 more bonds, right? So yeah, basically 2 more single bonds, 2 what H's. H's are not visible, as well as carbons in the majority of the cases, unless you are working with an aldehyde. But even in aldehydes, like you can skip showing the hydrogen, like in a lot of cases, right? Then here you go. So this is going to be your situation here. So there is CH2, right, originally. So, but now what we're going to have, once remove OH, we're going to receive CH left over, right? So on this carbon number 1, and carbon number 2 will turn from CH2 to CH, right? So as you see, so now they have only 3 bonds available, right? So consequently, we must have the 4th bond available to them, right? So if you think about that, so there is going to be the free electron, which kind of like is liberated after the departure of OH. And there is going to be also free electron that is liberated after the departure of one of the hydrogens, right? So it's going to be this free electron. So those kind of like black dots. Free electron, free electron. Now, excuse me, if they are connected, so they will make nothing more than a covalent bond. And it's very good for us because now both carbons are proper in terms of their valences. They all have 1, 2, 3, 4, 4 bonds. 1, 2, 3, 4, 4 bonds each. So now we made an alkene, right? So that's like what we were going towards at the very beginning. So that's it. So in this case, that's going to be your one and only product, right? So because you cannot have any more dehydration pathways except this one. So like because there is like, yeah, even though you have a couple of adjacent carbons to carbon number 1, right, which bears the OH group, so we cannot remove physically anything from carbon number 3 in terms of hydrogens because there are no hydrogens. So that's one case, and then you only get like one product, and then yeah, there is really like no application of Markovnikov's rule, right? So what you can do though for your practice is count how many carbons are attached total to sp2 carbons, right? So you have 2 sp2 carbons here, which make the double bond. So sp2, sp2. So they attach to themselves how many other carbons, right? So we cannot count like the sp2 carbons as the neighbors of themselves, right? So we only count the other carbons which are attached to those sp2 carbons, right? So so if we consider this carbon, so we cannot count this carbon as the one attached, right? So we need to count other carbons attached to the sp2 carbon. So those ones like stay put, so they just form a pair always, right? So like will be formed upon the dehydration of the alcohol for our intended purposes. So now we're going to other carbons, right? So like other carbons will need to be counted as the ones which are one bond away overall from either of those sp2 carbons, right? So let's maybe switch colors and then count those carbons, right? So if we look at this sp2 carbon, so this is not the neighbor, so we will not count that, right? So we're going to count other carbons, right? So which is going to be this one. So that's number one. Okay, so it is one bond away. This carbon is too far, for example, because there's two bonds away. So now we only found one neighboring carbon directly attached to this like first sp2 carbon. The second sp2 carbon has how many? So it has H attached to that, right? So another carbon. So what's one bond away? This carbon in red. So this carbon is too far. That one is too far because they are more than two bonds away already from this second sp2 carbon. So overall, we have two other carbon atoms attached to the sp2 carbons, right, in aggregate. So because we have two red dots here, which represent the carbons. So we're in a good shape. So this will be needed for the future application of the rule in more complicated structures. Okay, so now let's move on to a more complicated structure, right? So like you form one product. Okay, good. So now things will change. So if we, believe it or not, get to something even kind of a smaller molecular weight, and shorter length, but the details are there in the like arrangement of the OH group, right, in relation to various carbons. So here we go. So we're going now to look at the secondary alcohol, which is going to be looking like this, right? So 1, 2, 3, 4, 4 carbons. So it's going to be 2-butanol, right? On carbon number 2, there is the OH, which makes it an alcohol. So it's hosted by a butane. So consequently, you have altogether 2 on the second carbon. You have the alcohol, 2-ol, 2-butanol, right? So because your alcohol kind of the group is going to be located on carbon number 2, right? It's C and OH combination. So now 2-butanol is being dehydrated. So this carbon here with OH has how many? 2 adjacent carbons. That's 1 and 2. This is too far, right? Consequently, this carbon is out of consideration. So consequently, OH will be lost by this carbon, right? Let's call it number 2. Carbon number 1 can lose H potentially, right? Or carbon number 3 can lose H. So consequently, you can form 2 products. And we'll see if they're the same or not once we draw their structures. Okay, let's do that. So first of all, let's explicitly show the H's. That will be removed, right, in one case or another. So let's say we are doing 1,2 dehydration, right? So H and OH will be removed from 1 and 2 respectively. So what are we going to make is going to be 1-butene. 1, 2, 3, 4. Okay, 1-butene. That's what it looks like, right? So I'm just drawing skeletal structures because we need to be like proficient in them, right? So now plus the other product will be what? So 2 and 3 will lose OH and H respectively to make an alkene, which will be looking like this. Double bond, as we know, right, from the previous case. And that's it, right? So now you're going to have 1-butene versus 2-butene. So those are isomers. So they're almost the same, but you have the different arrangement of the building blocks. And the building block here, which has kind of like the differentiation, so to speak, which makes the differentiation between the two structures is a double bond, right? Its position is different. Here it's kind of terminal, as we call it, right? It's like on the end, right? And that's it. You cannot have anything here, right? So that's kind of like entailing the end carbon. So this is kind of the middle, right? So somewhere in the middle, literally like in the middle, I would say, double bonds. So because it's entailing like the middle carbons. So also 1, 2, that's where the double bond is hosted. Here, 2 and 3, that's where the double bond is hosted. So you have isomers here. So now, which one is major, which one is minor? So let's mark sp2 carbons with the different color. It's going to be, let's make it dark blue. As you see, so they are equal in terms of the count of sp2 carbons, so it doesn't like make sense to compare the sp2 carbons, right? So which are like present in those isomers. It's literally the same number, right? So the rule says that we are going to count the adjacent carbons, so like which will most likely bring the difference, right? So now we're going to count the overall number of the carbons which are attached to sp2 carbons. So this one has only H's, 0 carbons. This one has 1 carbon directly attached to that, 1 bond away, right? So now let's move on to the second product. So here we go. So we're going to have 2 sp2 carbons, right? 2 versus 2. Yeah, doesn't make sense to compare that. That's why the rule doesn't kind of like talk about the comparison of the number of sp2 carbons, right? So now let's count the carbons which are directly attached to sp2 carbons aggregate, right? So there's CH here, so it's not a carbon, and then this is a carbon. It's a CH3 group, right? So 1. So now moving on, so there's again CH here, and now we have another carbon here. Okay, great. So now overall you can see that here we have 1 carbon attached, right? Overall, in this compound, we have two carbons attached overall. So 2 is more than 1. Consequently, by the rule, so whoever, like, or whichever alkene has more carbons attached to its carbon-carbon double bond will win, right? So directly attached. So here 2 carbons are directly attached. Here 1 carbon is directly attached overall. So 2 is more than 1. So consequently, this one will be our major product, right? So this will become a major product. So this consequently will be the minor product. So yeah, this is our like application of the rule, right? So you can play around. So it's going to be like, again, a prompt to you to practice with the various alcoholic structures, maybe make some sort of like branched I mean chains here next, some kind of like branching going on next to the carbon with OH, right? So you can think up a lot of options, right? Even though, yeah, it seems difficult because it is a creative act at the end of the day. So, but again, it's going to be useful like for this course and beyond as well to just kind of like generate some sort of structures, right? So maybe you'll be able to generate ideas, for example, like based on this skill, right? So that you're practicing here, and then all of a sudden, so yeah, this is a transferable skill, right? It is just kind of like making something in your mind. So yeah, that might as well like be useful like in other courses or some kind of like other efforts in your life, right? Whatever you're trying to succeed. So yeah, that's our Zaitsev's rule. So that was our item number 1. So now let's move on to the next item. So our next item will be the formation of hemiacetals and acetals, as well as hemiketals and ketals. Okay, so let's take a look at this item, and then we'll incorporate that into the review-like item, which is going to be the multi-step synthesis, because it will like entail several steps which need to be performed before making those famous hemiacetals and acetals and hemiketals and ketals. Okay, so now let's take a look at some examples, right? So we're going to kind of like perform again. So in this case already the multi-step synthesis, because we are going to take a look at 2 steps, right, which are needed to, for example, go from an aldehyde to an acetal. So let's take a look at some aldehyde molecule, which is going to be looking like that. Sorry, I'm gonna use just a regular black font here. So like this, right? So let's imagine that this is our aldehyde molecule. That's how we can show it actually, right? So that's your aldehyde molecule. Just kind of like show the double bond here, and then you will be all set, right? So because the educated person will understand that at this point there is going to be a carbon, right? So since it is a band, so to speak, right? So like which kind of is congruent with the fact that sp2 hybridization is on the carbonyl carbon of the aldehyde right here, right? So it has to be kind of like, what's the trigonal planar, right? So like triangle. So in here, we need to have, to complete the triangle, actually, we need to have the like H, right? Which can be implied or it can be shown if you want, right? So right now, we don't have like strict hard and fast rules, but just be aware that in literature, you might see aldehyde like that, right? So, or sometimes it could be like with an H. So which is what we're going to show for our educational purposes, right? So we have C here with an H, double bond O, so carbonyl, C with an H, aldehyde, right? So this is like another carbon as usual, right? Some sort of like CH2 in this case. It could be maybe like a phenyl ring, whatever, right? So now we're going to add an alcohol to that. Let's just make some kind of like alcohol with a different number of carbons, right? Which is going to be maybe, let's make it like isopropanol, right? So according to our general example, we're going to form the OH bond, and then we're going to form the CO bond. So that's going to be the results of the what's it called, hemiacetal formation, which happens in acidic conditions. H plus is the sign of the acid because acids provide, right, H plus. They kind of like, what's it called, they lose H plus, right? They're proton donors, in other words. So now let's show the final product, which is going to be known as the hemiacetal, right? It's kind of like semi something, right? Semi, and acetal, it's kind of like from aldehyde, right? Like you have like aldehydes, which are finished with an L. Like this one is, for example, it's butanal, right? Al or Al at the end. So, and then you have acetal, like al at the end. So now, anyway, let's show the product finally. So maybe I can show the carbon explicitly, right? So as we can recall, it will undergo the rehybridization, right? It will be like turning from sp2 to sp3. So we'll form the OH, done, right? So let's show this bond explicitly. CH will survive. And then finally, we need to form this CCH2, kind of also survives, as well as this like huge tail, right, from 3 carbons. And then we have CO bond. So let's show it. CO, this oxygen here on the bottom, right? That's the one. It has also the isopropyl. Show that. So now you have your hemiacetal. So we'll not be kind of like concerned with the naming properly, but we just need to recognize that it is a hemiacetal, right? So just the type of the structure. So with its particular features, right? So typically, I guess the best way to see them, right, it's going to be like the practice, right? So you can, again, so you can do the self-practice, so to speak, right? So you can generate those structures by yourself as long as you can like recall in your mind what's an aldehyde, right? So let's make some aldehyde. That's why those worksheets, right, that we have been having in our class were like prompting you, okay, well, perform some particular reactions, but like here is the restriction, right? So your like aldehyde should have 7 carbons at least, right? Or total. So your alcohol should have like 4 carbons at least, for example. So yeah, things like that. So yeah, also you can convert, you can think about, okay, well, what's an alcohol, right? So it kind of like prompts you to convert your knowledge, right? Or to go from the like word, right, alcohol, right, to the structure, right? To go from the word, which is like aldehyde, to the structure. So now this is going to be now our reactant, right? So which is going to be used as the next stage. And we can just continue here actually, right? So we'll again be like using the same alcohol. Sometimes it's the case, right? Sometimes it's not the case, but it shouldn't startle you either way. So that's going to be another molecule of isopropanol. First molecule, now second molecule is added to the product of the first stage. So these arrows are the first stage, and this is our product, right? So now in the second stage, this product will be used as a reactant, right? And the second stage, we'll just extract it from the reaction mixture, let's imagine, and then we just use again acidic conditions, reversible process. And now we're going to eliminate water molecule as a result of this process, like that. OHH, or maybe H and OH, right? So doesn't matter, the result will be the same. You'll form the new CO bond and then the water will be eliminated. You can show the water elimination under the arrow, minus H2O, so that's okay. And then you're mostly going to be concerned with the product of the organic nature, which is going to be looking like this. So CH survives, CO with the isopropyl originally put there survives. So now OH is gone, free electron. H is gone, free electron. Electron connect. Oxygen with a dot and the isopropyl is here. All right, so now we're going to make the bond. like here. So that's the bond, the covalent bond. So that is going to be your acetal. So the ketal formation is very similar actually. So for the convenience of writing, so what I can do is that it's going to be a little bit like new explanation type, right? But like way. So, but here we go. So check this out. So you are just going to make essentially one change, right? If you want to, let's say, like explain to somebody, right? So like, this is fine. So we are going to just erase something and then track it, right? So let's erase this hydrogen, right? So and now you make a ketone, right? So you have this bond just without anything specifically shown on it, right? So like no chlorine, no bromine, no H. So this has to be CH3 particularly, right? So now you have a ketone. Maybe let's make something different, right? So let's put the like couple H's here, right? So that's your ketone now anyway, right? So it's going to be the same principle. OH bond will be formed, CO bond will be formed, right? So that's going to be the result. And now, instead of this hydrogen, we are going to have our ethyl. Let's maybe actually put it into the blue. Oh, no, let's make it purple color. So that's your purple ethyl right here, two bonds. Purple ethyl. Now this is going to be your hemiketal. Hemiketal. So next, we are going to use the second molecule of alcohol, kind of like everything is the same except literally this purple check mark, so to speak, right? So you are going to have also the like hemiketal will be also like reacting with an alcohol, right? Isopropanol here, and also the water will be released, OH and H minus H2O. So this reaction will be carried out with the presence of isopropanol as a reactant, obviously, in the acidic environment. And now we're going to form all the same bonds, except here you have not the, you have the blue check mark, and then here you're going to remove your H and show this purple check mark. So now this is going to be your hemiketal. So not hemiketal, but full ketal. So that's going to be our ketal. Ketal is now formed. So yeah, that's it. So that's like basically how those like four reactions work, right? So they are multi-step synthesis technically because we have two steps here. So and then for multi-step synthesis, like one of the things, right, where people get confused is that how like do we use like reactants there, right? So like basically, so if you want to visualize it like in simpler terms, let's imagine that our reactants are letters. So I'm going to clear everything and go to the multi-step synthesis. It's going to be item 3. Previous one was item 2. So here we go. So let's imagine you have some kind of reactant, right? Reactant, let's call it A, right? So then you apply some conditions, whatever it is. Sometimes they're kind of like dubbed as delta. And then you make compound B, right? So in a multi-step synthesis, you would continue, right? So what's going to happen is that now this compound B, which in this case, it is a product, right? So, but now it becomes a reactant at the next stage, next step. Now we have the multi-step synthesis because we already have two arrows, not one. We have some other conditions, whatever it is, right? Like delta 1, like different from delta like 0. So now we make C. So then we can continue. So we can apply another set of conditions, right? So maybe like delta 2, and then we can make D and so on, right? So BC relationship, so this is a reactant, this is a product. CD relationship, this is a reactant, this is a product, right? So things like that. So you can think about, again, analogies in life, right? So like the farm produces eggs, right? So eggs seem to be the product, right? But when you make like omelet from eggs, eggs are kind of like the starting material, and then omelet is the like the product, right? So like eggs to omelets, so transition, like think about that, right? So as a real life example. All right, so now let's take a look at our real life chemistry examples. And in this situation, we're going to take a look at the multi-step synthesis, which will be starting. Let's start with, I would say, let's start with an alcohol, right? So let's imagine we are going to have an alcohol like that. right? So with NOH. So it's secondary alcohol, and now we're going to like undergo dehydration, right? So and here you have some review things as well. So dehydration can be like done in the presence of H2SO4 under 180 degrees Celsius, right? So now you're going to do the dehydration. So here you will see that this carbon with OH has two adjacent carbons to that. So each of them has an H, right? So you can potentially lose HOH like this, or you can lose HOH like that. And you will form the bond here, double bond here or there. So, but no matter what you do, so even if you like write out those two possibilities of the two compounds, right? So you will see the same compound. So your product will be an alkene, right? Double bond here or there doesn't matter. It's going to be the same product, right? So because you can easily rotate one product by several degrees, and then you will have them superimposed, right? So that's why this kind of like spatial thinking will be like helpful, right? Like when you draw, you can rotate them like whilst you draw, right? So I can literally like draw like the rotation from one situation to one phase to another. So, or you can rotate them in your mind. So it's a little bit like more difficult skill, but it's also possible. So now you have an alkene. What can you do with an alkene? So with an alkene, you can perform the actually, let's make it a little bit more different, a little bit more difficult. So let's imagine that there is going to be a isopropyl group here, like so, right? So here you still have an H, right? So, but now by the Zaitsev's rule, you are going to make different, but you're going to make isomers. Because in one case, so let's say you lose H and OH here, and now you have the double bond kind of on the like rightmost side, and this one has the isopropyl, right? So now another case when you lose H and OH from these two carbons, right? So then you will have another isomer. So check this out. So that's your other isomer. That's a double bond right here. So you see the position of double bond is different in this ring. So it's kind of like farther away from this junction, and then here it's closer away to this junction, right? So that's like a way to compare them and then realize that they are different in terms of position of the double bond, right? So these are two isomers. So which one is major, right? So now let's count the carbons which are attached to our sp2 carbons in aggregate. So let's imagine that the sp2 carbons are like blue, for example, right? So that's sorry, they're supposed to be blue. It's one sp2 carbon, that's another sp2 carbon. That's one sp2 carbon, that's another sp2 carbon. So both molecules have two sp2 carbons. Now, let's see how many carbons are attached in aggregate to sp2 carbons. Here we have one, that's just an H. That's just an H here, another one. So two carbons total are attached directly via one bond to the sp2 carbons in aggregate, right? So here in aggregate, we have more carbons attached to blue carbons. So this one is CH. Now it has only one attachment. Okay, good. So this one is C, quaternary carbon, doesn't have any H's. It has attachment to like one carbon and another one. So total in aggregate, via one bond, three carbons are attached to sp2 carbons. Three is more than two, so this is supposed to be completely blue, so I don't want to make any confusion. So this is blue right here. So now let's count the red dots, right? So which are attached carbons. So two carbons total, two red dots. Three carbons total, three red dots. So three is more than two. Consequently, this one wins. It's more substituted in terms of the carbons, right? So more carbons are attached in aggregate to sp2 carbons here. So via one bond away from either of those carbons. So now this is going to be the major product, more carbons. So this is going to be our minor product. So now imagine that you are going to move to the next stage, and then you're going to use the major product, right? So that's how that's what you isolate, right? Using like various purification methods. And then you are going to move on to the next step, right? So now what we're going to do is we'll take this major product and then we'll use it at the next step, right? So let's imagine the next step will be the hydration process, right? So what's going to be happening there? So let's take a look. So here we go. I'm going to do the hydration process. All right, so I'm going to redraw. Maybe I'll go just down and then redraw and draw there. Okay, so that's the one. So now this is our reactant, right? In the hydration process, let's imagine, right? So I'm going to add HOH or water, right, in H2SO4. So as a result, we're going to use now here not Zaitsev's but Markovnikov's rule, right? It's about attachment, addition reactions, right? And then H and OH will go somewhere. So hydrogen, according to Markovnikov's rule, will go to the carbon with more H's. This carbon here has no H's. This carbon here has only one H, right? So hydrogen will go to this carbon. So now let's draw the product of this step. So this carbon here turns into CH2. So CH turned into CH2 because of attachment of one more H. So now here, this guy used to be C, right? But now it has to attach to itself NOH. So that's our alcohol. The kind of alcohol is that? That's going to be tertiary alcohol, right? So now let's imagine that we are going to make it undergo next steps, such as ether formation, right? So with a different alcohol molecule, let's imagine that we are going to have a phenol as our other alcohol, which we use for the condensation leading to the ether formation. Conditions? Done. Okay, so now ether formation. So here you're going to do some removal, right, of water. So you're going to remove, let's say, OH from here. So the other alcohol will lose H, not OH, because the H2O will be removed, or HOH, right? And then you'll have the formation of the bond. I'm going to show the liberated electrons in red. So as you see, you're going to form carbon, oxygen, carbon bond. COC is a sign of the ether functional group. So it's going to be a little bit complicated to draw it, but we can do it. This is going to be the tetrahedral carbon, right? And phenyl. All right, so that's it. So that's our ether COC, right? So you have the ether, like kind of complicated product, right? And the project, right? So, but we made it possible. So, yeah, that's like where we are. So let's now imagine that we have a little bit different situation, right? So, and then we indeed start with an alcohol, right, that has no isopropyl, right? So what's going to happen in this case? So let's imagine we're going to have the alcohol like that, right? So no matter how we do the dehydration, so of this alcohol, you will get only one product, right? Which is going to be looking like that. So that's going to be your one and only product. Cyclohexene, as we call it, right? If you have a double bond here or there, so you can just rotate it by several degrees, and then you will have the superimposition of the two like molecules, and then you actually form only one molecule, right? So if you try to hydrate it, right? So hydrate this alkene, so you are going to have only one possible alcohol, which is going to be looking like that, right? So then what you're going to do is that you can apply some different steps, right? Such as oxidation. Remember, so the oxidation of the tertiary alcohol doesn't give you like aldehydes or ketones, right? So the secondary alcohol will give you a little bit more like leeway in terms of the oxidation processes, right? So that's going to be why? Because we're going to review them, right? So oxidation of the secondary alcohol. So what does it lead to, right? So it will lead to the formation of the ketone. Let's show that. Oxidation agent. So pretty much only get like one possibility, like in our course, once we oxidize the secondary alcohol, that's a ketone, right? So The H will be lost and H will be lost. So you can just show them as such, right? So then, as you might sense, the carbon-oxygen double bond will be formed as a result. And then we're going to have the following molecule. So this is our like carbon, the locus of our attention. So it used to be CH here, right? So, but now H is lost. And from OH, we lose H. What's missing? The double bond. So that's going to be your ketone, cyclic ketone, right? So that's where you are in terms of the multi-step synthesis. Just another thing to review. So if you somehow, somewhere, right, have the, let's say, primary alcohol. So this will be a little bit more flexible in terms of the oxidation processes. So then that's what we can show. Okay, so let's show some random primary alcohol, which is going to be like this. So OH, right? So, and here you have it, right? So this is going to be your CH2 piece, technically, right? So it can be oxidized. So with the mild oxidation agent, mild oxidizing agent, so we're going to get the aldehyde, right? So H will be removed and H will be removed. So as a result, you are going to get CHO, CHO, right? So 1, 2, 3, all three carbons will stay, they will stay put. This is the fourth carbon or the first carbon, actually, if we count, right, by the nomenclature rules. So we'll be looking like that. So O and show the H here, right? So that's going to be your aldehyde, which further can be oxidized with like a strong oxidizing agent, right? So either way, if you oxidize or with a oxidize with an oxidizer or oxidize with a strong oxidizer, you oxidize your like aldehyde, you are going to obtain the carboxylic acid. How is it going to be done? So that's how it's going to be done. Those carbons survive 1, 2, 3. So now carbonyl carbon stays carbonyl, but it's going to be a little bit different. So literally you need to make one switch, right? So you will like kind of like remove H and switch it to NOH, or you will insert oxygen between C and H, right? That's another way to imagine that. And you are going to make this like OH bond here. So like OH group will be here now. That's the OH bond I'm trying to show. So that's it. This is going to be your carboxylic acid, right? So if you use a strong enough oxidizing agent, you can go directly from the aldehyde, from the alcohol to the, what's it called? To the acid, right? So that's typically going to be also like a shortcut. If we have a strong specifically, it's going to be a specific environment, right? Strong oxidizing agent will give you the carboxylic acid directly from the alcohol. Mild oxidizing agent will give you the aldehyde from the alcohol. So just something to keep in mind, right? And then if you oxidize the alcohol, for us, like no matter like what oxidizing agent you use, if you oxidize the aldehyde, no matter what oxidizing agent you use, you are going to get the carboxylic acid, right? So that's just a sequence: alcohol, aldehyde, carboxylic acid. Sometimes you have a shortcut from alcohol to carboxylic acid. Or maybe sometimes you have the aldehyde and you want to oxidize it, you will only get the carboxylic acid. So these are kind of like opportunities that are presented by this multi-step synthesis. So at this point, we are done, and thank you for your attention. Bye, everyone.